So in this video, we are going to mainly focus on SN1 and SN2 reaction. So here you can see chemical reactions of haloalkanes. So haloalkanes will show three types of reactions. First one is nucleophilic substitution reaction, second elimination reaction, and third is reaction with the metals. First, we will see nucleophilic substitution reaction. The meaning of nucleophile is they are electron-rich species. So, usually they are represented as Nu minus. So, here you can see haloalkanes are substrates. In this reaction, if you see, Nu minus is called as nucleophile and haloalkanes are called as the substrate, and here X minus is called as the leaving group. Leaving group departs as halide ion. So X will be leaving as X minus. So this is X is called as the leaving group. So why it is called as nucleophilic substitution reaction is nucleophile will be substituted in place of halogen. Therefore, it is called as nucleophilic substitution reaction. And one more important point here is halogen is bonded to sp3 hybridized carbon. So here this carbon is sp3 hybridized. So halogen is bonded to sp3 hybridized carbon. Next, this table is very important. So here what you have to mainly focus is on these reagents KCN, AgCN, KNO2 and AgNO2, that is potassium cyanide, silver cyanide, potassium nitrite, silver nitrite. So all this four are called as ambident nucleophile. So ambident nucleophile meaning is they will have two nucleophilic center, that is so cyanide. So in cyanide you can see carbon can also attack alkyl group. Nitrogen can also attack alkyl group. So there are two nucleophilic center. Same way in nitrite also, nitrogen can attack alkyl group or oxygen can attack alkyl group. Therefore here two nucleophilic centers are present. So here you can see in the table potassium cyanide. Potassium cyanide is ionic in nature. Because of that, it will be breaking as K plus and Cn minus ion. So minus is present on carbon. So now here carbon is also electron rich and nitrogen is also electron rich. But carbon will be attacking R and it will form RCN. So if Cn is attached through carbon, if it is attached to R group, it is called as cyanide. Whereas in silver cyanide is covalent in nature. Therefore, it will not break as Ag plus and Cn minus. So here now nitrogen will be having lone pair of electron. So this nitrogen will attack R group. As a result, RNC will be formed. So nitrogen will be forming bond with R. So then it is called as, if it is NC, then it is called as isonitrile. Same way potassium nitrite. So in potassium nitrite, this is ionic in nature. Therefore, it will be breaking as K plus and NO2 minus. So negative sign will be present on oxygen. So this oxygen will attack R. So you will be getting RON double bond O, which is alkyl nitrite. Whereas silver nitrite, this is covalent in nature. So therefore the bond doesn't break. So now what will happen is nitrogen is going to attack R group. So therefore you will be getting RNO2, which is nothing but nitroalkane. So here you can see cyanides and nitrites possess two nucleophilic centers and are called as ambident nucleophile. So cyanide group is a hybrid of two contributing structures, that is two resonance structures are present. So you can see this is one resonance structure and this is another RS, that is resonance structures. So here carbon has negative sign and nitrogen will be having lone pair of electron. So here carbon will be attacking this carbon of the alkyl group and a bond is formed between carbon and carbon. So why nitrogen doesn't attack? So nitrogen also has a lone pair of electron, but nitrogen will not attack carbon. Only this carbon is attacking. So what is the reason? So the reason is given here. Carbon-carbon bond is more stable than carbon-nitrogen bond. So here the carbon-carbon bond which is formed, so this is more stable. Instead, if C and N bond is formed, this is not stable. So this is more stable. So next we can see here mechanism. SN2, that is substitution nucleophilic bimolecular. SN2 meaning is substitution nucleophilic bimolecular reaction. So this is a second order reaction, meaning is the rate is proportional to concentration of two reagents, that is nucleophile and haloalkanes. So you can see this is the reaction. So OH minus is called as nucleophile and this is alkyl halide. So nucleophile will attack the carbon. Simultaneously you can see Cl minus will be leaving. So a transition state will be there. In the transition state you can see the bond is formed by OH and here the bond is breaking simultaneously. And this transition state is unstable. Why it is unstable? Because carbon is bonded to 5 atoms. You can see 1, 2, 3, 4, 5. So this carbon atom is bonded to 5 other atoms. Therefore, it is highly unstable in nature. And this is the product formed. So since here nucleophile is attacking the carbon atom from behind. So here you can see the configuration will be inverted. Inversion of configuration will take place in SN2 reaction. So here you can see this is a single step reaction. So if you see the reaction, all this are taking place in one step. So if it is single step, the same step will be rate determining step. So rate determining step will be the slowest step. Since only one step is there, this itself will be the rate determining step. And here you can see as a result configuration will be inverted. Inversion of configuration will take place. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and outgoing leaving group. Such structures are unstable and cannot be isolated. Thus, in the transition state, carbon is simultaneously bonded to 5 atoms. So already I told you that. So this is the transition state where carbon is bonded to 5 other atoms. Therefore, it is highly unstable and this cannot be isolated. Since it is unstable, remember transition state is unstable. Therefore, this cannot be isolated. And then configuration. So what is configuration is spatial arrangement of functional groups around carbon is called as configuration. So this is carbon atom. So arrangement of groups around it is called as configuration. So next we will go for the order of reactivity of SN2 reaction. So the order of reactivity is for methyl it is greater, then primary, secondary is greater than tertiary. So why it is, we will see here. So this is methyl group. So you can see C, H, H and H. So you know that nucleophile will be attacking from backside and halogen will be leaving from this side. Since it is attacking from behind, so here if smaller groups are there, so attacking the carbon atom becomes easy. Whereas here you see in the primary carbon, so in the primary carbon a bigger group is there. So because of that, so entering the nucleophile attacking the carbon atom becomes little difficult. Whereas in secondary carbon, if you see, still bigger groups, so 2 bigger groups are there. Therefore, nucleophile attacking the carbon atom becomes difficult. Whereas in tertiary carbon, you can see 3 big groups are there. Therefore, it becomes very, very difficult for the nucleophile. See here, 0% chance for the nucleophile to attack carbon atom because of steric hindrance. Steric hindrance meaning is there are bigger groups. So, therefore, nucleophile cannot attack the carbon atom. So, therefore, for the order of reactivity will be for primary halide it is greater, secondary and then tertiary. And before that there is methyl group. If it is methyl, so the rate of reaction will be fast. Then primary, then secondary and then tertiary. Next we will go for SN1 reaction, that is substitution nucleophilic unimolecular. 1 meaning is unimolecular reaction. So it is a first order kinetics because the rate of the reaction depends on concentration of only alkyl halide. So we will see why. So here let us see this example what they have given. So this is tertiary butyl bromide. So here we have a nucleophile. So nucleophile will replace this Br and you can see OH is formed. and this reaction takes place in two steps. So here you can see two steps. In the first step, what is happening? In the first step, you can see Br leaves us Br minus and a carbocation is formed in the first step. And in the second step, you can see nucleophile is coming and attacking the positive sign of the carbocation and it forms alcohol. So students, here the first step is the slowest step. So always remember that RDS, rate determining step. Rate determining step always will be the slow step. So here this is the rate determining step, and in the rate determining step you can see there is carbocation formation. So stable the carbocation, the rate of the reaction will be faster, and nucleophile is not seen in the slow step. It comes only in the second step. Therefore, the rate depends only on the formation of carbocation. So here you can see step 1 is the slowest and it is reversible. It involves CBr, that is the bond between C and Br breaks, for which the energy is obtained through solvation of halide ion with the proton of protic solvent. So here in SN1 reaction we are going to use polar protic solvent. So I have written the difference as well. You can go through this. SN1, it takes place in two steps. SN2, it takes place in one step. And here it proceeds through carbocation formation. Whenever carbocation is formed, you have to check for rearrangement. SN2, so it goes through transition state which is highly unstable, and here there is no rearrangement. And in SN1, polar protic solvent will be used, and here polar aprotic solvent will be used. And order of reaction, so you can see the rate of the reaction. Tertiary carbocation is more stable than secondary and then primary, whereas here in SN2 the rate of the reaction for primary will be more and then secondary and then tertiary. And in SN1 the rate of the reaction depends on concentration of only one reagent, which is alkyl halide. In SN2 the rate of the reaction depends on concentration of both alkyl halide as well as on the nucleophile. And here for the SN1 racemization takes place, that is you can see two types of product will be formed, whereas in SN2 there is inversion of configuration. So here you can see the rate, step 1 is the slowest step we have seen, therefore it is the rate determining step. The rate of reaction depends only on the concentration of alkyl halide and not on the concentration of the nucleophile. Greater the stability of carbocation, greater will be its ease of formation of alkyl halide. So it depends on stability of carbocation. And then, so here I have written, see the order. So tertiary alkyl halide is, the rate will be more, and then secondary and then primary. And then allylic and benzylic halides show high reactivity towards SN1 reaction, because you know that in allylic carbon, see here if a carbocation is formed here, it is stabilized by resonance. Even here in benzylic halide, so if a carbocation is formed here, it is stabilized by resonance. Therefore, they prefer to undergo SN1 reaction. So for the given alkyl group, the reactivity of the halide Rx follows the same order in both mechanism, that is Ri, Rbr, Rcl and Rf. So the meaning is living group. So you know that Ri and Rbr if you take, so I will live faster when compared to that of Br. Therefore, I will be good living group when compared to Br. And then comes chlorine and then comes the fluorine. So it is same for both SN1 as well as for SN2. So this will be the order of the living group. So I will be the better living group. I minus is the better living group. So now we will solve this example 6.6. In the following pair of halogen compound, which would undergo SN2 reaction faster? So students, here first remember this. For the SN1, the rate of reaction for tertiary it will be more, and then secondary and then primary, and you have to check the stability of carbocation. For the SN2, primary is greater than secondary, which is greater than tertiary. So this is tertiary. So this will be tertiary. And then you have to check about the steric hindrance. For SN2, you have to check for the steric hindrance. So now we will see the question. So now we will compare in this two, and we will see which would undergo SN2 reaction faster. So here halogen is attached to this carbon, and here halogen is attached to this carbon. So here you know that SN2 mainly depends on steric hindrance. So here this is the primary carbon, and here this is the secondary carbon. So what is the order of the reaction for SN1? For SN1, the order of reaction is, here you can see primary greater than secondary. So here this is the primary carbon, and here it is the secondary carbon. Therefore this will undergo SN2 faster. And here we will see, so this carbon is primary carbon, this carbon is also primary carbon. So both are primary carbon. And then you see the leaving group. So iodine and then chlorine, which is good leaving group. I minus is good leaving group. So therefore this is better, this undergoes SN2 better than the other one. So here you can see iodine is better leaving group because of its large size. It will be released at faster rate in the presence of incoming nucleophile. Predict the order of reactivity of the following compounds in SN1 and SN2 reaction. The 4 isomeric bromobutanes. So here you can see these are the 4 isomers of bromobutane I have written. So we are going to check SN1 and SN2 reaction. So the rate we are going to check. So here SN1 we can see, for the SN1 reaction what you have to check is stability of carbocation. So stability of carbocation we will see. Stability of carbocation tertiary is greater than secondary, which is greater than primary. So here you can see this is tertiary carbon, this is secondary carbon, and here this is primary carbon, and here it is primary carbon. So this will show more SN1 reaction. This comes next. So that is why we are writing order like this. In this two we are going to compare. Both are primary carbon atom. But here you can see, since there is a branch over here, the inductive effect will be more here. Because of more inductive effect, the stability of carbocation also will be more. Therefore, this will show more rate of reaction for SN1 compared to this. So this is 1, this is 2, this is 3, and this is 4. So that is what here the order is given. You can check. Next we will check for SN2. For SN2 what you have to check is steric hindrance. So here you see more steric hindrance is present. And here you can see steric hindrance. Secondary also there will be more steric hindrance. For SN2 you have to go for primary, which is greater than secondary, and then which is greater than tertiary. So you have to check in this two. In this two again, because of branching, so this will undergo less SN2. Therefore this is number 1, this is number 2, this is number 3, and this will be number 4. And then second reaction. So this is the second reaction they have given. See, I have written the structures for that. So this is first. So first we will check for SN1. So for SN1 what we have to check? Stability of carbocation. So this carbon is primary, this carbon is secondary, this carbon is also secondary, and this carbon is tertiary. So tertiary will be more stable for SN1. So this is more stable, first position. Now in this two we have to compare. So in this two, which is more stable? So here you can see 2 phenyl rings are present. So resonance will be more here. Therefore stabilization also will be more. Stability of carbocation is more here. So this is number 2, and then this is number 3, and then primary carbon will be number 4. Next we will check for SN2 reaction. For SN2 what you have to check is steric hindrance. So here you can see steric hindrance is more for tertiary. And then secondary, if you compare, here the steric hindrance is more because of 2 phenyl ring. Here there is only 1 phenyl ring and 1 methyl group is present. So here steric hindrance is more compared to this. and here the in primary carbon steric hindrance is less. Therefore, for SN2 reaction, this is first place. Primary will be first, and then second, and this is third, and this is fourth. So this is what is explained here. So you can go through it. So next we will see about stereochemical aspects of nucleophilic substitution reaction. Now let us learn about stereochemical aspects of nucleophilic substitution reaction, which is very important. So first let us see what are optically active compounds. When plain polarized light is passed through certain organic compounds, those organic compounds will rotate plain polarized light either in the clockwise direction or anti-clockwise direction. If it is rotated in the clockwise direction, it is called as dextrorotatory, and you can represent as small d or plus in the bracket. If plain polarized light is rotated in the anti-clockwise direction, then it is called as levorotatory, and how you will represent is small l or minus in the bracket. So here you can see plane of plain polarized light produced by passing ordinary light through Nicol prism is rotated when it is passed through the solution of certain compounds. Such compounds are called as optically active. And then you can see if it is rotated in the clockwise direction, it is called as dextrorotatory. And how do you represent it? D or plus symbol. If it is rotated in the anti-clockwise direction, it is L form, and you will represent it as minus. And then molecular symmetry, chirality, enantiomer. So here what you should know is, example, this is the carbon atom. So to the carbon atom, if 4 different atoms are attached, so all these are different atoms, then this carbon is called as asymmetric carbon, or it can also be called as stereocenter, or it is also called as chiral carbon. So remember these 3 words: asymmetric carbon, or stereocenter, or chiral carbon. So this compound is non-superimposable on its mirror image. Then these compounds are called as optically active. How to identify whether the given compound is optically active is, this is how you can identify. That is, you have to check whether this carbon is attached to 4 different atoms or not. If it is attached to 4 different atoms, then it is optically active. So here you can see, if all the substituents attached to the carbon atom are different, then the mirror image of the molecule is not superimposed on the molecule, and such carbon is called as asymmetric carbon, or it is called as stereocenter. So all this I have condensed and I have given here. So just revise this. And you can see this box, chirality. The object that cannot be superimposed on its mirror image is called as chiral. So non-superimposable mirror images. So here you can see these are non-superimposable on its mirror images. So such objects are called as chiral objects. And here these are superimposable. So such objects are called as non-chiral objects. So superimposable meaning is take this and place on this one. So exactly they will fit on each other. That is called as superimposable mirror images. So if it is superimposable, they are called as non-chiral, or they are called as achiral. If it is non-superimposable, then it is called as chiral. So let us see 2 examples what they have given here. The first example is propane 2-ol. So this is propane 2-ol. So check whether it is optically active or not. How you will check? Just now I said that, see whether the carbon atom is attached to 4 different groups or not. So this is the carbon atom. See, these 2 are similar and these are different. So all 4 should be different, only then it is optically active. But here these 2 groups are similar. Therefore this is not asymmetric carbon. Therefore this will be optically inactive and they will be superimposable on its mirror image. So here you can see, so this and this you can superimpose on one another. Meaning is take this and place on this molecule. So exactly they will fit on each other. So these two are superimposable mirror images. Therefore, they are optically inactive. Why? Because two similar groups are present. And one more example is given here, butane 2-ol. So again check whether they are optically active or not. This is carbon atom. See, all the groups which are attached to this carbon atom is same or different. CH3, C2H5, H, OH. So all are different groups. Therefore, this is optically active and they are not superimposable on its mirror image. So this and this you check whether you can superimpose on one another. So they are not superimposable because CH3 and here you have C2H5. So exactly they are not fitting on each other. So they are non-superimposable mirror image and they are optically active. And some more examples are given, you can see. Examples of chiral molecule. So these examples are given, so you can just make a note of it. So these molecules I have written here. So first one is 2-chlorobutane. So butane means 4 carbon atoms should be there. 1, 2, 3, 4. So 2-chloro means chlorine atom is present at the second carbon. So check whether they are optically active or not. So this is the carbon. So see whether 4 different groups are attached. Chlorine, CH3, H, C2H5. So 4 different groups are present. Therefore, it is optically active. Second example, what is given? 2,3 dihydroxypropanol. So this is the structure. So check whether it is optically active. This is carbon, hydrogen, then aldehyde, OH, CH2OH. All the 4 groups are different. So this is also optically active. Third example. So here bromochloroiodomethane. So this is the third example. So carbon atom, see here, bromo group, iodo group, chloro group, hydrogen. All are 4 different groups. Therefore, they are also optically active. The fourth example we will see, 2-bromopropanoic acid. So this is 2-bromopropanoic acid. So to the carbon you check hydrogen, methyl group, bromo group, acid group. So 4 different groups are present. So therefore this is also optically active. So they have given some examples. Make a note of it. Next, what are enantiomers? The stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. So here these two are non-superimposable images. Therefore these two will be enantiomers. So remember the definition, what are enantiomers. And then enantiomers possess identical physical properties, namely melting point, boiling point, refractive index. They only differ with respect to rotation of plane polarized light, that is dextrorotatory or levorotatory. So if it is asked, enantiomers, they differ in physical properties, then you have to say no, it is wrong. So they differ only in rotation of plane polarized light. Then coming to racemic mixture. So what is racemic mixture is, if both dextrorotatory compound and levorotatory compound, if it is present in equal amount, then it is called as racemic mixture. The process of conversion of enantiomer into racemic mixture is called as racemization. Identify chiral and achiral molecules in each of the following pair. So we have to identify which is chiral and which is achiral molecule. So chiral molecule meaning is, I already said you that the carbon atom should be attached to 4 different groups. So this is carbon. You can see here hydrogen, OH, bromine and methyl group. So 4 different groups are there. Therefore this is chiral. And here you can see same groups are present. So this is achiral. And here also 4 different groups are attached. So this is chiral. And here you can see 2 same groups are present. Therefore this is achiral. And in this is the carbon atom. This is bromo group. This is methyl group. And this side hydrogen. And one more is ethyl group. 4 different groups are present. So this is chiral. And here you can see this is the carbon you are going to check. One side you have this group. One side you have bromine. And here hydrogen and hydrogen. H2 you have to write one up and one in the below. So it becomes hydrogen and hydrogen. Same groups are there. Therefore, this will be achiral. Is that clear? And then retention. So retention we will see when no bond to the stereo center is broken, the product will have same general configuration of groups around the stereo center as that of the reactant. So here you can see this is the molecule what is taken, that is 2-methyl butane 1-ol. So here when it is reacted with HCl, what is happening is this bond is broken. This bond, that is, this is not attached to stereo center. This is stereo center. So stereo center bonds are 1, 2, 3, 4. So these bonds are not broken. Leaving this, the other bond is broken. When the other bond is broken, then the configuration is not going to change. So read once again. When no bond to the stereo center is broken, so stereo center bonds are not broken here, the product will have the same general configuration of groups around the stereo center. Therefore, configuration of this and this will be same. There will be retention of configuration. One more thing what you should remember here is, see here, configuration can be same, but optical rotation can be different. So note this minus sign and plus sign. So this is dextrorotatory and this is levorotatory in nature. Even though configuration is same, optical rotation can be different. And then inversion, retention and racemization. So here this is the compound. So here you can see there is inversion of configuration. So inversion of configuration is, so here you can see hydrogen is on one direction and methyl is on this side, whereas here you can see it is on the different side. So inversion of configuration can take place, or there can be same configuration, retention of configuration. Racemization meaning is if both plus and A and B, that is this is A and this is B, if they are in equal percentage, 50% of A and 50% of B if it is present, it is called as racemic mixture, because plus and minus symbol can cancel and it will become optically inactive. So see here, if 50 is to 50 mixture of A and B is produced, then the process is called racemization and the product is optically inactive. Why it is inactive? One isomer will rotate the plane polarized light in the direction opposite to the other. Therefore it become optically inactive. So one more important concept, make a note of it, that is SN2 mechanism and SN1 mechanism. We are going to see the stereochemistry. That is here check what is the type of carbon atom which is taken. So here you can see this is secondary carbon. And here you check what kind of carbon atom is present in this example. So in this example also it is secondary carbon. So here secondary carbon atom is showing SN2 mechanism, whereas here again the secondary carbon is showing SN1 mechanism. So how you will differentiate this? So always remember that if it is tertiary carbon, definitely it will show SN1 mechanism. If it is primary carbon, then it will show SN2 mechanism. If it is secondary, then it can show SN1 or it can show SN2 depending on the type of nucleophile. That is what you have to check. So here both are secondary carbon atoms, but one is showing SN2 mechanism and other is showing SN1 mechanism depending on the type of nucleophile. I'll show you the difference. So in the first one, this is the example. What is the example? 2-bromo-octane. So 2-bromo-octane is allowed to react with sodium hydroxide. Then you can see octane 2-ol is formed with OH group occupying the position opposite to that of bromide had occupied. So here sodium OH group is a strong nucleophile. So sodium hydroxide will produce OH minus, which is a strong nucleophile. Always remember, strong nucleophile will show SN2 mechanism. So OH minus will attack this carbon from behind. Therefore you can see the configuration is going to change. Inversion of configuration will take place in SN2 mechanism. Whereas in SN1 mechanism, it is racemization. Why it is racemization? Because in SN1 mechanism, you know that carbocation will be formed. So carbocation is planar in nature. Therefore, you can see nucleophile can attack from behind or it can attack from front side. So if since some will attack from back and attack from front, so you can see 50% of one compound and 50% of other configuration. Because of that, you can see racemic mixture will be formed. And here you see the example what is taken is 2-bromobutane. Hydrolysis of optically active 2-bromobutane, which results in the formation of butane 2-ol. Hydrolysis meaning is water is used here. So water is a weak nucleophile. So remember, the nucleophile used here is weak nucleophile. If it is weak nucleophile, always remember it will show SN1 mechanism. So that is what, if it is secondary carbon, you should check what is the type of nucleophile which is used. So here it is strong nucleophile which is used, and whereas here hydrolysis meaning is water is used which will produce weak nucleophile. So that is why it is showing SN1 mechanism. If it is SN1 mechanism, then it is racemic mixture, that is 50% of one configuration and 50% of other configuration will be shown. Whereas in SN2 it is inversion of configuration. So configuration will be inverted. So learn these two examples. So students, I hope you are understanding it clearly. So go through it, make a note of all the points. So here you can see all the points I have noted down, and also here at the side I have written, and wherever possible I have highlighted it. So take down all this and revise it. Prepare well for your examination, and if you have any doubts, leave in the comment section, students. I'll meet you in the next video. All the very best.